The detection of flooded areas from high-resolution synthetic aperture radar (SAR) imagery is a critical task. To address this, a novel differential attention metric-based network, DAMNet, is proposed. DAMNet comprises a weight-sharing Siamese backbone and a temporal differential fusion module. The backbone is split into multiple stages, each consisting of temporal-wise feature extraction, cross-temporal change attention, and temporal-aware change enhancement. The proposed DAMNet is evaluated on the S1G floods dataset, which is more diverse and richer than existing datasets, containing various flood events. Experimental results demonstrate that DAMNet outperforms recent methods on the S1G floods dataset, achieving 97.8% overall accuracy, 96.5% F1 score, and 93.2% IOU. The main contributions of this paper are the proposal of DAMNet, the design of the temporal differential fusion module, and the creation of the S1G floods dataset. The proposed DAMNet architecture consists of three key modules: temporal-wise feature extraction, cross-temporal change attention, and temporal-aware change enhancement. The temporal-wise feature extraction module, comprising two parallel branches, models locality and long-range dependency, as well as local context, using an overlapping embedding layer, pyramid reduction module, and multi-head attention module. The representations obtained are then fed into the cross-temporal change attention module, which employs an attention mechanism to model long-range dependency between representation tokens of multi-temporal images, generating effective change information. The change features are then fed into the temporal-aware change enhancement module, which explores the semantic correlation between the representation and change feature of each temporal image, enhancing the change features. The module shares a similar architecture with the temporal-wise feature extraction module, except for the drop of the overlapping embedding layer and pyramid reduction module. The outputs from the temporal-aware change enhancement module are integrated using a temporal differential fusion module, yielding the flood map. The proposed DAMNet architecture is designed to capture complex relationships between multi-temporal images and generate accurate change information. The novel overlapping embedding layer, cross-temporal change attention module, and temporal-aware change enhancement module contribute to the performance of the proposed DAMNet. To accurately identify waterbody changes, a class token is added to the preflood branch, obtaining high-level semantic information of waterbody changes. The temporal differential fusion module integrates the change features of multi-temporal images using an absolute difference operation at multiple scales, generating the flood map. The network is optimized using a joint loss function, consisting of contrastive loss and dice coefficient loss, considering the class imbalance issue. The S1G floods dataset, consisting of 5,360 image pairs, is introduced to achieve diversity in flood events. The dataset is divided into training, validation, and testing sets, and the proposed DAMNet is compared against state-of-the-art methods on the global flood detection task. The research paper discusses the development of DAMNet, a change detection network designed for global flood events. It leverages multi-scale image features and the U-Net decoder to detect changes. The authors compare DAMNet with state-of-the-art methods on the S1G floods dataset, reporting the performance metrics such as precision, recall, F1 score, overall accuracy, and intersection over union. The results show that DAMNet achieves a comparable recall to CNN-based methods and the highest score on precision in F1, with a lower computational complexity. The paper also includes visualizations of detection results for intuitive comparisons. The authors propose the DAMNet architecture for flood detection and inundation mapping, utilizing Sentinel-1 Saudi Riyal images from Nebraska and Iran to demonstrate its effectiveness in large-scale flood inundation mapping. An ablation study is conducted to verify the effectiveness of key design elements, including the overlapping embedding layer, which provides a significant improvement in flood detection accuracy. The research paper introduces a novel model for flood detection, known as DAMNet, which utilizes Sentinel-1 Saudi Riyal image pairs. This model incorporates various modules such as CTCA to capture global contextual information and TACE to address information loss. Additionally, the inclusion of a semantic token enhances the model's ability to differentiate between waterbody changes. The paper presents promising results, with DAM-Net achieving an overall accuracy of 98.8%, an F1 score of 95.3%, and an intersection over union (IOU) of 92.6%. An ablation study highlights the significant contribution of each module to the model's performance. Furthermore, the research discusses the development of a novel method for flood detection using deep learning techniques. The authors introduce a new dataset, S1G floods, which encompasses diverse environments including wetlands, riverine areas, mountainous regions, urban and rural areas, and vegetation. This dataset is beneficial for developing flood detection methods that exhibit excellent performance and good generalizability. The results demonstrate that CNN-based flood detection methods performed relatively poorly on the newly created S1G floods dataset compared to effective vision transformers, with an IOU score that was 7.8% lower. The authors recommend improving the quality of the images used in the S1G floods dataset, utilizing information from another SAR sensor more effectively, and acquiring images from drones or cloud-free optical remote sensing sources to increase the accuracy of water body interpretation.